Is a long strike structural variation and partitioning of the convergence-related shallow crustal shortening across scales during orogeny, insights from the eastern Himalaya Sikkim. So during the talk, if you find that the slides are not changing or the animations are not moving, please stop so I can take, we can take it be on the same page. Is a long strike structure variation and partitioning of the convergence-related shallow. This is a diagram showing the different insights from the eastern Himalaya. In this talk, I'm going to during the talk, if you find the convergence, the slides are not changing or the animations are not accommodate the convergence, shortening structures form. So I can along the narrow take it be on the same page. Is a long strike structure variation and partitioning of the convergence-related shallow. This is a diagram folded thrust faults and thrust-related insights from the eastern Himalaya. In this talk, so during the talk, if you find the convergence, the slides are not changing or the animations are not accommodate the convergence of the shortening structures form. So I can along the narrow they can be on the same page. Is a long strike structure variation. For example, this is a geological shallow. This is a diagram folded thrust faults and thrust-related insights from the eastern Himalaya. In the lithology along the strike of the glide horizon, presence of transverse zones and long-term variations in the erosion rates. So now let's see what happens to the most active orogenic belt closer to home. The Himalaya in the lithology along the strike of the glide horizon, India presence of transverse zones in the late Cretaceous long collided with the Asia approximately 50 million years. So now let's see what's creating the most active orogenic mountain belt on the Earth's surface. The Himalaya in the lithology along the strike of the glide horizon, India presence of transverse zones suggests that a long collided with the Asia approximately 3,400 kilometers. So now let's see what's happening with the most Asia orogenic mountain belt on the Earth's surface. The Himalaya in the lithology along the strike of the glide horizon, presence of transverse zones suggests that a long collided with the Asia approximately 52 million. This is a geological line. So now let's see what's happening with the most Asia, which shows the same characteristics of structures which are folded along the strike of the glide horizon, which branches out from research with the Asia. Of the greater Himalayan sequence, which is marked in this pink color, are lesser in the western Himalaya, And the tectonic windows marked in this green color are more in number in the eastern Himalaya. We can also see this lateral variation at a much smaller scale. For example, this is a geological
of the greater Himalayan sequence, which is marked in this pink color, are lesser in the western Himalaya,
of the
and the tectonic windows marked in this
also
green
they are
color
laterally discontinuous.
are more in
So now let's
number
ask this question:
in the
how
eastern
such
Himalaya.
variations in the
We can
structural
also see this
architecture of
lateral
the Himalayan
variation
mountain belt
at a much smaller
affect the
scale.
total minimum
For example,
shortening
this is a
estimates.
geological greater Himalayan sequence,
This is a plot
which is marked in
where
this
showing
pink color,
the
are lesser in the western
total
Himalaya,
minimum shortening
and
estimated
the
from
tectonic
the
windows
different
marked in
transects
green
of the
color
Himalayan
are
mountain
more
belt.
in
So now let's
number
ask this
estimated
question:
how
using
is
sectional balance cross sections.
We can also see
The
this
different
lateral
colors are
variation
indicating
For
shortening from
example,
the
this is
different
a
tectonostratigraphic
geological
units. This is a
sequence,
plot.
which is marked
There are
by
two
showing
points I'd like to drive
lesser
here.
in the
Number
western
one
Himalaya,
is that approximately
tectonic
4 different to 900 kilometers of shortening has been estimated from these different transects, which are the kind of colors that indicating shortening that the lateral variation in the structural architecture is also being reflected in the minimum shortening estimates. And number two, that the shortening has been estimated from these different transects, which are the shortening estimated by the perimeter data, indicating that like the many methods, the lateral variation in the structural architecture is also being reflected in the minimum shortening. For example, and the outcome skills that the shortening structure from this cannot be incorporated into the biological section because they remain below the resolution at which the cross-sections are constructed. Another limitation is that the hanging wall cutoffs are assumed to lie at the blind in eastern Sikkim, giving rise to lateral variation in the structural architecture within 15 to 20 kilometers, providing a perfect platform to address this set of questions. To answer them, I have done detailed fieldwork in this region, collected more than thousands of planar data and lateral variation in the linear data, and based on the fieldwork, I found that the northernmost thrust the main central thrust questions. It carries upper amphibolite to granulite faces, gneissic rocks, and detailed sandstone of the Shivalik group, and the main frontal thrust carries Shivalik in its hanging wall. Sandstone
of the Shivalik group.
Based on the
main frontal
representative
thrust carries,
dominant
Shivalik in its hanging
all
wall.
the thrust sheets are interpreted
the Shivalik group.
based on the
main
so
frontal
based on
thrust
this
carries,
data sets
Shivalik
and
in
the
its
available
hanging wall.
geophysical data, I have constructed
Shivalik group.
based on the
main
so based
frontal
on this
thrust
data
carries,
sets
Shivalik
and the
in its
available
hanging wall.
geophysical data, I have constructed the results based on the so based on the background data sets and the available for I have constructed the results based on the background. So a balanced cross-section is different from a simple geological cross-section because it is admissible, so it is restorable and viable. So what does these different terms mean? So admissibility indicates that the structures that you are portraying or drawing on the cross-section should be similar to the structures that you observe in the field. It is restorable, meaning that the deformation can be pulled apart, means it can be restored to an undeformed state. Viability indicates that the bed length or the area remains consistent between the deformed cross-section, between the deformed and restored sections. And the shortening can be calculated by subtracting the deformed length from the restored bed length. To constrain the regional transport direction, I have used mineral stretching lineation data collected from the internal thrust sheets and the hinge line data of outcrop scale folds from the full land part of the orogeny, and I constrained this to be the regional transport directions. So I have constrained a regional balanced cross-section along this transect. First, I have constructed the topographic profile along this transect. Then I have projected all the planar data on the cross-section by calculating apparent dip along the line of cross-section. Then I have marked all the thrust faults based on the field mapping. And then I have calculated the thickness of the thrust sheets by incorporating the mean foliation, orientation, and the outcrop thickness of the lithologies. Based on that, I have determined the footwall template. Then I have divided the orientations into different dip domains, and then I have used the kink method to draw the kink axis. So based on the parameters that I have just talked about, I have arrived at this deformed geometry, where the foliation dip subhorizontally, which I used to arrive at the regional dip. Based on the exposed thicknesses of the MCT and the PT, I determined the depth to the detachment, to the décollement over here to be 13 kilometers. Additional evidences are coming from the CCP receiver function images. Based on the changing in orientations from steeply dipping to a gently dipping, I constrained the location of the footwall ramp. Additional evidence is coming from the CCP receiver function image, and dip to the MHT below this duplex structure I have constrained to be 10 kilometers. Additional evidence is coming from the geoelectric data set. Now, what we see is that the internal thrust sheets are folded and exposed in the foreland in the Lavalo-Legao Klipa. This is the Darling duplex whose root thrust is the Pelling thrust, and this is how the overlying thrust sheets are folded. So therefore, there has to be a footwall structure which has folded this overlying thrust sheets. So the question is, how do I constrain that blind structure? To do that, first I actually looked at the transects that lie east and west of my study area, and I see that there are duplex with foreland dipping horses present in the footwall of the Ramgarh thrust. Additionally, I looked at the cleavage bedding relationship, where I find that the cleavages are gentler than the bedding. So based on that, I constrained that the blind duplex structure must have a fold and dipping component. Therefore, I tried that, and I constrained the geometry of the blind structure to be a hinterland dipping to a foreland dipping. As it is blind, there are n number of possibilities. So I try out with a scenario where the foreland dipping horses are carrying the Darling group of rocks, which are these green color rocks. So now when I try to restore them, they are restored as back thrusts, which are kinematically not possible in the scenario. So therefore what I did, and additionally, if you restore the structures, so based on palimpsestic reconstruction, this is the proposed northern extent of the Gondwana Basin. Now, if I restore this structure, this is where it ends. So such variation, lateral variation in the initial width of the sedimentary basin in such short distance is unrealistic. So what I did, I looked at the adjacent transects again, and I found that the foreland dipping horses also have Gondwana and Baksa component in it. Therefore, I tried that, and I could arrive at restored geometry where all the thrust faults are restored in the right configuration. However, I still do not know if this configuration is kinematically viable or not. To prove that, I first constrained the sequence of thrusting. Based on the retrograde monazite ages, we constrained the earliest activity on MCT to be around this time period. The lutetium-hafnium ages of the Barrovian sequence, which lies in the hanging wall of the Pelling-Munsiyari thrust, the garnet growth on a prograde path occurred between this time period, 14.6 to 10.6. And all these isogrades are folded by the lesser Himalayan duplex, indicates that they must have formed younger than 10.6. So based on this, I constrained overall a four-landward propagating thrusting sequence. To do that, I look at deformation in a forward modeling way, where I imposed deformation on the last form structure first, followed by its successive formational order, which shows that MCT formed first, followed by PT, then the Darling duplex, then Ramgarh thrust, then the foreland dipping horses formed, followed by the hinterland dipping, and then MBT and MFT. So with that, by comparing the restored bed length and the deformed bed length, I estimated a total of 403 kilometers of shortening, which is a minimum shortening, I must say. Now on comparing shortening from the adjacent Western Sikkim, and I found that Eastern Sikkim records 47 kilometers lower shortening than the Western transect. Now, based on the existing hypothesis, I tried for an explanation for this small-scale lateral structural variation. As the thicknesses of the different stratigraphic units did not really vary laterally between these two transects, so this factor cannot really explain this variation. There are no known transfer zones lies between these two transects, so therefore this also cannot explain this variation. The 10 beryllium data shows that the erosion rate at the millennial scale did not really vary laterally much. It varied from north to south. Therefore, the lateral variation in the erosion rate may not have played a role in this lateral structural variation in the Sikkim Himalaya. So now let's look at the cross-section more carefully. There is a frontal ram, MHD frontal ram below this Rangit duplex, which is 2 kilometers thick. which actually generated enough structural culmination to expose the duplex in western Sikkim, whereas the corresponding footwall ramp is only 400-meter thick in eastern Sikkim, which did not generate enough structural culmination to expose it. And the corresponding footwall ramp lies farther north. So the lateral variation in the location and the thickness of the MHT frontal ramps has played a role in controlling this lateral variation at a smaller scale. Just to summarize what we have talked so far, based on the construction of a regional transport parallel balance cross-section, I have estimated approximately 403 kilometers of total minimum shortening from the eastern Sikkim transect. Although partially blind, the lesser Himalayan duplex still accommodates a significant amount of shortening, which is 157 kilometers. And the small-scale lateral variation is also manifested in the total minimum shortening estimates, and the lateral variation in the location and the thickness of the MHT frontal ramp have contributed to the along-strength variation, structural variation in the Sikkim Himalaya. Now that I have constrained the large-scale structural geometry of the thrust faults and estimated its shortening contributed, let us examine, can penetrative strain reconcile the missing shortening that is there in the Himalaya? Now, to document penetrative strain, I have collected quartz-rich rocks from all the exposed thrust sheets. In the field, I have oriented my sample with respect to the tectonic foliation, which tracks the XY plane of the strain ellipsoid. Now, to get the X direction, I have used the mineral stretching lineation. So now I have got the XZ thin section parallel to the mineral stretching lineation and perpendicular to the foliation plane, and the YZ section perpendicular to the mineral stretching lineation. I have also cut a third section, which is 45 degrees to the mineral stretching lineation. In the absence of mineral stretching lineations, I've also used correlation lineation and hinge line orientations to arrive at the XZ thin section. For total, I have analyzed 297 thin sections that were cut from 102 rods. So I have estimated penetrative strain from crystal plastically deformed quartz grains. I have digitized approximately 80 to 120 quartz grains per thin section, and then using the IISER software, and then I have used the shape matrix eigenvector method embedded in the IISER software to calculate the mean strain ellipse. Now, when I'm looking at thin section, this is how the foliations looks on the thin section, but the foliation has a dip in the field. So to correct for this, I have incorporated the aberrant dip of the foliation in the thin section plane. The 2D strain data coming from 3 such thin sections per sample is used to arrive at the strain ellipsoid geometry, and I have used a Mathematica best fit strain ellipsoid program to generate that. So along with the penetrative strain, I have also studied the deformation microstructures of all the thrust sheets. So here I'm just briefly going to summarize some of the salient features that I have observed. In the internal thrust sheets, the quartz dominantly records deformation by undulous extinction, subgrain formation, dynamic recrystallization, indicating a crystal plastic deformation. Whereas in the external thrust sheets, quartz grains dominantly record deformation by elastico-frictional mechanism. They dominantly show fracturing. So to understand how the penetrative strain is distributed at the origin scale, I have plotted the 2D strain ellipses estimated from the exit in sections on the cross sections by incorporating the apparent dip of the foliation that I have just talked about a few slides earlier. What we can see is that the penetrative strain magnitudes remains higher in the internal thrust sheets, and it progressively decreases toward the external ones. The variation in the deformation mechanisms in quartz might controls this variation in the strain magnitude. For example, that the dominance of crystal plastic deformation in quartz in the internal thrust sheets has resulted in higher plastic strain in the internal thrust sheets, whereas the lack of crystal plastic deformation in the external ones resulted in lower strain magnitudes in the external thrust sheets. And if you look at the 2D strain ellipses, you can see that they are folded along with the thrust sheets in which they lie to the same degree, so indicating that they might have formed prior to the thrusting event. A similar trend I have also observed in the Western Sikkim transect, where the strain magnitude is decreasing towards the foreland, and the 2D strain ellipses are folded along with the thrust sheets in which they lie. To comprehensively understand the strain ellipsoid geometry, I have also studied the 3D strain ellipsoids. So I have projected all the strain ellipsoids on the cross section, on the two cross sections, and from the geometry we can see that the XY plane of the strain ellipsoids are subparallel to the tectonic foliation orientations, and they are also folded along with the thrust sheets, indicating that they have formed before thrusting. So now let's look at, so far we have looked at how penetrative strain varies across the full thrust belt. Now let's try to see what kind of pattern they might exhibit if we look at it within a thrust sheet. This is a plot coming from the MCT and the Pelling thrust, and from the plot we can see that the strain magnitude is kind of remains lower as we are high up in the thrust sheet, and it kind of increases as we move towards the basal shear zone. It increases within the shear zone, indicating that there is a strain localization that's happening along those discrete shear zones. Now, to demonstrate the kinematic sequence in which penetrative strain has developed within the thrust sheets, I'm going to use this cartoon, where this rectangle box indicates the geometry, the pre-deformation geometry of a thrust sheet, and we are going to use this reference circle to track deformation at the as penetrative strain. With shortening, first penetrative strain formed first, and with progressive shortening, there is folding and thrusting. At the time of thrusting, the deformation gets localized within the shear zone, and this is how I see rocks in the finite deformed state in the Sikkim Himalaya. I have already accounted for this shortening as we have discussed so far. Now what I'm planning to do is to account for this shortening. I already know this number, which is the strain magnitude for every samples. Now what I have to do, I have to convert them into a shortening percentage. To do that, I have calculated weighted mean of the strain magnitude for every thrust sheet. And then using this formula, I have actually converted them into penetrative shortening percentage. Now, to calculate the green scale shortening, I have integrated the penetrative shortening percentages with the base length of the corresponding thrust sheet to arrive at the green scale shortening. Now, when I do that, this is how the green scale shortening is distributed for in every thrust sheet for Western Sikkim and for Eastern Sikkim. There are 2 points I'd like to mention here. Number one, that the green scale shortening is decreasing from the internal thrushes to the external one. And I have estimated approximately 101 to 116 kilometers of green scale shortening from the exposed thrush sheets. However, adding green scale shortening from penetrative strain to the shortening estimated from balanced cross sections, it's not kind of a straightforward task, as we have to consider the orientations of the strain ellipses. So now let's say if we have a thrush sheet which is exhibiting layer parallel shortening. Now, when you remove the layer parallel shortening from the thrush sheet, the base length increases. Therefore, so when you add this shortening from layer parallel shortening, it increases the total shortening of the thrush sheets. Like if you add it with the large scale shortening, totally it increases. On the contrary, when you restore strain from thrush sheets which are recording layer normal shortening strain, the base length decreases. So now when you incorporate this shortening, like add this shortening to the large scale one, then it will decrease the total minimum shortening. In the Sikkim Himalaya, the internal thrush sheets, all these thrush sheets are actually recording layer normal shortening strain in the finite deformed state, where the strain ellipses are parallel to the thrust plane. The XY plane of the strain ellipsoids and the long axis of the strain ellipse is parallel to the thrust plane, indicating that they are recording layer normal shortening strain. Whereas in the external part, the thrust sheets are recording layer parallel shortening. Now, if we add all this shortening that we have estimated to the large scale shortening, it will decrease the total minimum shortening by 13%. Therefore, this study illustrates that the non-incorporation of crystal plastic penetrative strain with shortening estimated from balanced cross-section does not necessarily underestimate the full thrust-belt shortening, as it is kind of considered to be one of its limitations. Now the question is, where did the shortening go? So we propose certain explanations where there could be this missing shortening, which are as follows. The number one is the shortening from the Tibetan Himalayan sequence is typically estimated between these two structures, which is the South Tibetan Detachment System and the Indus-Sangpo Suture Zone. However, there are THS rocks lies far the south of it. So incorporation of these structures, shortening from this THS clippa will increase the shortening estimates coming from the Tibetan Himalayan sequence. Recent studies have actually showed that there are multiple thrusts within the Greater Himalayan sequence rocks. So there is one such thrust has also been recently discovered by Chirantan Chakraborty. Their work has shown that there are thrusts within the GHS. So incorporation of these structures into the balanced cross section will increase the shortening coming from the GHS. There are outcrop scale folds which might be recording a lot of this Himalayan shortening, which are unaccounted for. So that could be one explanation. There could be a higher possibility that the majority of the Himalayan deformation may have been eroded away and which has not been actually accounted for. And recent study show that the Shillong Plateau, which lies southeast of Sikkim, records recent upliftment. So the Shillong Plateau might also accommodate some of the Himalayan shortening. So this could be some of the factors which might provide some explanation for the missing shortening. the penetrative strain may not be, at least in the finite deformed state, cannot provide an explanation for the missing shortening. So therefore, to conclude, what we have talked about so far is that the lateral variation in the location and thickness of the main Himalayan thrust frontal ramp can explain the small-scale variation that we observe in the structural architecture of Sikkim Himalaya. This lateral variation is also reflected in the minimum shortening estimates, where Eastern Sikkim, with partially blind Lesser Himalayan duplex, records 47 kilometers lower shortening than the Western Sikkim, where the duplex structure is fully emergent. Penetrative strain accommodates 101 to 116 kilometers of shortening. However, incorporation of that shortening to the large-scale shortening is not a straightforward task, as the orientations of the strain ellipses need to be considered, and due to the dominance of layer normal shortening strain in the finite deformed state, the incorporation of the green scale shortening to the large scale shortening will decrease the total minimum shortening by 13%. And this study illustrates that the non-incorporation of penetrative strain with the shortening estimated from balanced cross-sections does not necessarily underestimate the full thrust-belt shortening, as it is considered to be one of its limitations. So with this, I'm going to conclude the presentation. So thank you for listening, and if there are any questions, I'll be very happy to answer them. So. Is everyone there, or am I the...
Jyotirmoy, are you there?
Yeah, for a second I got spooked.
Hello, Jyotirmoy. Okay, I think Jyotirmoy is somewhere. Thank you very much, Chirantan.
Is it Professor Bose?
Yeah, thank you very much.
Thank you, sir.
So, you have given an excellent talk. However, I'm sure that there will be a lot of queries from the audience. So now the house is open for discussion. Yeah, I am. Please go ahead.
Okay, am I audible?
Yeah.
Yeah, okay. So Chirantan, I have a question in terms of you are measuring strain from the, from thin section. So if the area you are working in, if you see there are several orogeny transverse structures, like several across orogeny folds are there. So in such situation, how much is it valid to see the finite strain or the finite ellipse shape and assume that this ellipse is giving the estimation of the north-south shortening?
Yeah, that's a very interesting question. See, so when I tried to measure penetrative strain, I was trying to measure the total change in shape that has happened during the entire orogeny, during the entire Himalayan orogeny. So obviously, you have this north-south folding, as you correctly pointed out, in the Sikkim Himalaya. We have, which is a much more younger event. So when I measured the strain, they are actually, so the strain ellipsoids and the penetration, it's actually it's parallel to the orientations of the, it's actually tracking the dominant tectonic foliation orientations. Okay, so now, so in terms of the effect of that those north-south structures on the strain magnitude, I couldn't see, but those structures, so I haven't shown such plots, but they have actually affected the orientations. So now what I did actually, incorporated all the strain onto the cross-section, and from cross-section actually I have undeformed, keeping their orientation in check. So the orientations of the x-axis typically is along the transport direction. So the x-axis is not varying. So x-axis, which is kind of expected in that kind of scenario. So it's for LNS kind of strain, not for LPS strain. So it's along the transport direction. The y-axis is actually perpendicular to the regional transport direction. So which is kind of indicates in a way that the effect of those north-south structures could be minimum. So that's how I restored it, because they have their long axis are along the transport direction. However, as you said, there is, I looked at the orientations of these strain ellipsoids, if they have been affected by the north-south folding or not. And when I plotted them, the data from the both sides, they are actually showing that they have been affected by the folding, in the sense that their orientations have been modified, but along the flank of it. But otherwise, the way I restored it, that effect was minimum, the north-south.
Okay, I mean, the orientation can remain same, but suppose you are stretching an ellipse by a factor of 2 and then compressing it by a factor of 1, then you will still get that the ellipse is stretched along your initial stretching direction. But it kind of underestimates the shortening or extension, isn't it?
Yeah, but it will be very difficult to decouple it. So in the finite deformed state, see, we don't have this incremental strain stages being preserved actually. So obviously there are a lot of events going on. There is so the overall strain pattern shows that they formed, prior to thrusting, but when thrusting is happening, there is strain localization is happening, then there is folding event, then there are footwall structures which are folding. So as a result, the strain is getting overprinted by all these different events. But if you look at when you are measuring strain from these rocks, they are overall tracking the dominant foliation. So the effect of that will be there, but it was negligible, could not be picked up. So so as a result, so when you are restoring them, so you are kind of getting strain which may have accumulated, at least in terms of the strain geometry, have accumulated prior to the thrusting.
Okay. Thank you. You really.
I hope I could
really
answer.
well. Yes,
you
explained really well. Thank you.
Thank you, Ayan. I'm sorry, I just my internet went down for a briefly, so that's why I could not attend the last portion of the talk. So, any other question?
Chirantan,
yes, sir.
I have just a query. It's not a question. So your study that is you have done, it is completely based on a model.
Yes.
The model is Coulomb-Boyce model, I believe.
Yeah.
Okay.
It's a critical.
Just I have not finished it.
Sorry, sir.
So the thing is, I understand that there are different models to explain these structures, but how could you really model Coulomb-Boyce of a deeper level rocks that you find in the hinterland part of the Lesser Himalaya?
Thank you, sir, for asking this question. This is a very interesting question. I'll try to answer, and I hope I can convince you. So the model based on which I have kind of tried to explain the overall structures in the Sikkim Himalaya is a critical wedge taper model. So, which kind of follows Coulomb's criteria. However, if you look at Professor,
so this is an assumption, right?
Yeah.
At the initial stage, this is an assumption.
Yes. So now, if you look at some work by the work by Chappell, 1978, where they have all so he studied the wedge behavior only, but the material that he used was a plastic material, like the rocks are deforming plastically. So now, if you look at the Chappell 1978 results, and the observations are very similar to the Davies et al. 1983 observation. So overall, although the materials being different, they show similar characteristics in terms of...
These are of very shallow crustal level.
Huh?
These are of very shallow crustal level structures.
Yes, these
you can
are...
compare this thing with accretionary prism. I don't mind if you agree, if you compare this thing with the frontal part of the Himalayan belt. But my question is, how do you incorporate this Coulomb-Wedge model structure to the hinterland structures?
See, I'm not really making an assumption about Coulomb-Wedge. But
when you go for this cross-balance section, then you on the behind you are assuming this model, right?
Sir, I'm making a couple of assumptions, which I will try to explain. So the one of the assumption. So we assume a critical taper wedge, as you said correctly, and obviously critical taper wedge that Davies et al. Is about non-cohesive Coulomb wedge, Coulomb criteria. So the assumptions that we are making, I have made while making a cross section, which other people also make while drawing, is that which I have talked about, is that the shortening, like the outcrop scale shortening structures and penetrative strain kind of structures are not incorporated, and the hanging wall cut off actually lie at the present day erosional surface. So in terms of how the wedge behaves, it makes a taper, and it forms a topographic slope, and it also makes a then you have a decolma tape, and then the way critical taper is being explained. So that is also there. But what I will say to your question is that although if you change the material, from the non-cohesive Coulomb to a plastically deformed, so the same pattern will remain consistent, and that has been shown by the Chappell 1978 study and the Davies et al.
But if you do mechanical model, just this is a suggestion from my side. If you do some mechanical model where you can deform material plastically, you cannot develop this thrust the way you develop in Coulomb wedges.
See, the shear zones are forming. We can see the shear zone.
Shear zone you can form in a different way also, right? You can form shear zone in the overturned limb of a fold as well.
Yes. Depending on what depth you are forming that.
Queries, we can talk later as well.
Yes.
But it was a very nice talk.
Thank you, sir.
This I should appreciate. Okay.
Okay, Professor Bose, thank you very much. Any other question from younger colleagues or our teachers?
Experience.
Yeah. Professor Mukhopadhyay, Professor Shetty, or Professor Saha?
Mondal is not there?
Professor Mondal, I don't see.
Okay, I think he left.
Well, Jyotirmoy, can I?
Yes, please, sir. Please, sir.
Well, first of all, let me congratulate Chirantan for presenting an articulate talk on a topic which has interested, evinced interest in many of the listeners over here, including myself. One or two clarifications I would just ask is, first of all, you mentioned that there is a blind duplex in real life. So what are your controls for bedding data for the blind duplex? How do you get the bedding measurements for one which is blind?
So, sir, I have used the surface geology to constrain the blind structure. So I don't have any, there are no geophysical images, like seismic images or anything available to actually know how the structures could be like the blind structure. So I had to look at the indirect evidences. So the way I went about the bedding orientations within the horses, I kind of followed the way, the models for the different type of horses, the way bed will be oriented in a hinterland dipping horse versus a foreland dipping horse versus an antiformal stack horse. So I kind of went with that. So this is a model, this is one of the way which can explain the surface geology. There could be many other ways by which you can also explain. You can come up with a very different one than mine and can explain the same surface geology that we observe in Sikkim Himalaya. So just to add on top of this, this is one of the non-uniqueness aspect of constructing a balanced cross-section is that, how do we go about constraining the subsurface structures? So balanced cross-section gives at least a little better constraint than a simple geological, a normal cross-section, because it can eliminate lot of subsurface geometries that are geologically may not be a very viable one. However, still it's a non-uniqueness, still a non-unique component of a construction. So the recent advances that has happened very recently by a group of workers from University of Pittsburgh, so the Nadine McCurry's group, where they have actually what they are doing to have a more constraint on the subsurface geometry. They kind of subject the models to two different additional checks, which are flexural kinematic modeling of the cross-section, and the other one is a thermokinematic modeling. So what they do, they try to deform it flexural kinematically. So they put a load and erode. So when you deform a thrust, so putting a load and which is flexuring the lithosphere, and then you remove, you erode the material and dump it in a foreland basin. And with this, you deform the entire sequence and see if you can match the topography that you are seeing on the surface. Can it match the foreland stratigraphy and the timing or not? If it can, then they subject this model to another check, which is the thermokinematic. So with this sequence, with this geometry, with this subsurface geometry, with the kinematics, can it produce the thermochrometric edges based on the modeling, and then it can match with the measured thermochrometric edges? And if there is a match, it means that the subsurface geometry and the kinematics may be more you're more confident about the model. So in this case, I didn't have those other two checks. So this is just purely based on surface geology. And now if I subject this to maybe flexural kinematic, maybe there will be things which will not be matching. So as a result, I might have to alter the subsurface structures and the kinematics to explain. So that will be my answer to your question.
Yeah, nice. See, for example, in a simple-minded way, I would possibly think that a borehole would possibly better justify whether there is a blind duplex or not. But apart from that, I was happy to see while you were explaining the missing, within quote and unquote, missing shortening, you mentioned about outcrop scale folds, right? Yes. So, those are essentially buckling folds, or?
See, I did not really measure contribution from outcrop scale folds, because there are buccal folds. Professor Bose's work shows there are buccal folds. We have seen buccal folds, but I have not measured the contribution from such folds. It's almost impossible to do it. So I just tried to estimate the contribution at the much smaller scale, which is the microscopic scale, and which I found cannot really much explain the shortening, missing shortening in the Himalaya. So there has to be something else which might be taken care of, or maybe the crust has been subducted without leaving any trace. So that could be another thing. So so I did not really measure anything from outcrop scale.
What is your comment on, say, for example, if I say, if you see buckle folds on outcrop scale, why we should not also consider seeing the large scale buckle folds?
Yeah, see, in order to, like, you know, I think there was some study in the Nepal where they kind of, using simple shear, they kind of model, like, you know, how much outcrop scale folds might be accommodating. But I don't know if there are any ways by which this contribution could be measured. The balanced cross section, the problem with the balanced cross section, because of its scale, such structures, unless they are large enough in terms of their order of folding, like, they cannot be really portrayed on the cross section. So as a result, those shortening structures remains unaccounted for. All the works have shown there are plenty of outcrop scale folds, very tightly folded structures. So those like shortening, like, you know, shortening contribution from structures, if we can measure, that might hold an explanation for the missing shortening.
Jyotirmoy, am I taking too long time?
No, sir. Please go ahead.
Please
It's
go
a
ahead.
very interesting discussion. Please go ahead, sir. We have plenty of time.
Yeah, Chirantan, one other thing that bothers me is that when you are going for penetrative scale deformation, your measurements are based on crystal plastic deformation of quartz grains, right? But many of these rocks, especially in the lesser Himalaya, are say phyllosilicate rich also, right? So, I mean, how do you constrain the strain within them, penetrative strain within them?
Thank you. This is a fantastic question. This is like one of the questions, like, has a lot of people asked. And see, even if you just consider, if you don't think about the other minerals, just think about only one mineral, which is the quartz. Apart from crystal plastic deformation mechanism, there are other competing mechanisms at play as well. Like in the internal thrushes, there were precious solutions I have observed. So that's also accommodating some amount of the convergence related, like, you know, that forming as a response to the convergence. But I couldn't account for that strain, like strain accumulating due to precious solution. So as a result, I only focused on the crystal plastically deformed quartz. So the penetrative strain or the grain scale shortening that I have measured, it's actually the minimum one. There are so many mechanisms of quartz itself is also accommodating, and that was not unaccounted for. So this is a very minimum estimates of penetrative strain. And now, as you said, like, you know, there are other minerals, like, you know, there are plenty of mica there. They accommodates a lot of the strain. And so you can, like, do EBSD and all of that, which I have no idea about, and get an idea about the strain in those mineralogy, but I don't know how that can be, like, you know, used to really say how much shortening is accommodated, like, you know, how much shortening is recorded by those minerals as penetrative strain or by different deformation mechanisms. So that will be exciting if we can do that. But thank you for pointing out, like, the strain that I have measured, it's absolutely minimum. And at certain places, I have, like, you know, especially in some shear zones also, I have, because of the scarcity of relict quartz grains, I have used also, like, you know, some dynamically recrystallized quartz. So some of the early strain informations are gone. So these are very So the estimates that I have showed are very minimum.
Okay, I'm happy that you said that. I mean, because this also puts into doubt, say, your measurements measurements of the strain ellipsoid, in the sense that there is a lot of recrystallization as well as this penetrative strain accumulation.
So those are actually, I kind of interpreted them like, those are very like, only for MCT zone and the PT zone, where most of the grains, more than, I think, there were hardly 18 to 16 quartz grains, relic quartz grains I could find. And one of my colleagues, he could find, and which is not like statistically significant enough to like extract strain from them. So, so only in those two shear zones, like, we have measured it from recrystallized quartz, so which we are interpreting it as an incremental strain, not as a finite strain. But in these frontal parts, like, there are relic quartz grains present. So I kind of used them. And also, just to add to what you just said, I kind of avoided quartz grains which are exhibiting truncated boundaries due to pressure solution or are affected by fracturing. So I tried to only limit my analysis to those quartz grains in the rocks which are just showing signatures of plastic deformation. So I could just pick that information, because if there is a truncated boundary, then there are two mechanisms at play, and the shape is not just crystal plastically deformed one. So that will kind of add error to the analysis.
Right. Thank you, Chirantan. I mean, I enjoyed the talk and enjoyed the discussion as well. I mean, thank you so much.
Thank you, sir.
Right, and wish you all the best for your career.
Thank you, sir.
Okay, right.
Thank you, sir. Any further question?
This is Subrata Ghosh.
Yes, sir. Please go ahead.
Yeah, Dr. Parui, I have a few simple queries, like convergence you have talked about. So, as we know, in case of Himalayas, at the late stage of disappearance of the Tethyan Ocean, the compressive strain or deformation of the sedimentary rocks that were deposited in the ocean, when say just prior to the continent touch, shortening started from that stage. And another point is, we already know, this is quite established, that in the entire Himalayan belt, the convergence did not take place simultaneously. There was difference at one spot. The convergence between the two plates or the continent collision took place slightly earlier than in another place. These things were there, and for such type of balanced cross section, how the farthest two reference points were constrained properly or rationally in a very acceptable way. Okay, these three questions, and final question is.
Oh, sorry. So the first question is about the convergence. When did it actually start?
The shortening, particularly shortening of the rocks. They not only happened after the convergence or post-collisional convergence, they started much earlier also. Okay, so how these things were addressed in your studies? Did you think about those, and how would you reconcile? And
can you just repeat the third question? I kind of got mixed with the two other questions.
Third question was, okay, let me finish the last question, the fourth question. So the balanced cross section is along a straight line, okay? And you were constrained to make measurements along the traverses, which were not necessarily straight from the northernmost point to the southernmost point in your section. So how that was also reconciled, or how what sort of mathematically or
Yes.
this? Okay.
So thank you for asking this question. So I'm just going to answer them one by one, and please stop me, if I misinterpreted your question. So just to repeat, so your first question was about how. So the shortening started the moment the initial collision occurred, and how did I account for some of the early shortening? So so the collision, based on the current studies, which who try to constrain the age of collision, the ages are approximately the range is between 60 to 50 million years. Some people have 58, but I kind of gave an overall range, which is 60 to 50. So so since the collision, there are different models by which the collision might have happened. So there was a lot of shortening and thickening happened within the Tethyan Himalayan sequence early. So that I have not accounted for because I don't have access to those THS rocks in the Sikkim Himalaya, because the Tethyan Himalaya starts near the Gurudongma and it goes all the way to the Tibet. Don't have access. So I kind of taken the shortening estimates between the THS rocks from a study close to this transit by Rashbaker et al. 1992. So so from there, so I only constructed the balanced cross section from the frontalmost thrust to the GHS. So where the GHS deformation, the metamorphism happened in the Sikkim Himalaya, the work by Professor Shumit Chakraborty, Professor Mukhopadhyay, all their work shows that, the metamorphism, Shomhan Dashgupta sir, their work shows that, it starts around 30 million years, and the kind of the early deformation, the thrusting within the MCT happens around 23 million years. So I kind of constructed the balanced cross-section between these two lines, which encounters shortening within the GHS, LHS, and the sub-Himalayan sequence rocks.
Can I interrupt?
Yes, sir.
I'm Shantanu Bose.
Yes,
So,
sir.
what do you think about what happened during this period, from the collision, as you said, from 60 to 50 to 30 million years?
So there are one. So there was this.
Go ahead. In the meantime, you can also.
Yeah, sure. Just so Chirantan Chakraborty's work from Professor Malay Mukul's group, he showed, based on his work, that there was thickening and thrusting and thickening within the Tethyan Himalayan sequence was happening around 35, 40, 36, around that time period. And which kind of buried the greater Himalayan sequence rocks to a depth subjected to the metamorphism and all. I was reading a very interesting paper by Van Hensbergen, a 2012 paper which he published in PNAS. So where he actually talked about that. So what happened is this, that when India was coming to collide, so only the Tethyan Himalayan sequence part, which kind of detached from the GHS, and the rest of them, the India created an ocean, and first it actually collided with the Asia. So then, and recorded shortly.
This study is based on mostly on the paleomag studies.
Yes, that is based on the paleomagnetic data. And then what happened? Then the ocean got subducted, and then there was a hard collision, approximately around 25 million years.
Can I interrupt? Can I interrupt? Dilip Mukhopadhyay.
Yes, sir.
Okay. It is very unfair to ask Parui.
Yes, sir.
About that shortening during early phase, what happened at at the time of 50 minutes ago and all that. Because his work is on section balancing. That is after all the rocks have been assembled. His shortening is certainly not the India-Asia collision and pre-India-Asia collision and all that. So any question on that is, in my opinion, is out of the place.
No, sir, I thought if the speaker or the worker is aware of these things, it will bring completeness to his understanding. That was the main point.
He understands. He understands. There is no problem with that. He understands.
Yeah.
But from his work, he cannot estimate shortening right from the hard collision or soft collision or all that. He cannot do that.
I understand.
Right. So there is really no point having. That's a wider discussion involving many other things. Just as Santanu said that it is essentially based on paleomagnetic studies.
Yes.
And it cannot be incorporated in any kind of balance crossing. I know a thing or two about balance cross section.
Yeah.
Okay. About the other points,
Yes.
if you...
Sir, you asked about that. How did I? Because not all the road traverses will be along the line of cross section. That's a very fantastic question. So the way actually I went about it is that along the line of cross section, if my data is within 500 meter, so I kind of projected them along strike. If not, I kind of projected them as it is. Okay, so I made sure, because there is a structural variation laterally, so I don't project data which are like really far off. So typically all my roads that I have taken were close to along the line of cross section, but let's say over here that there was no other way to map this area because there were no roads. So I projected this data onto the line of cross section, which is typically a standard practice for drawing any cross section when you don't have data close to the line of cross section.
Thank you.
Thank you, sir, for asking this question.
Thank you. All the best for your future.
Thank you, sir.
So I think, Professor, there are two Mukhopadhyays there. So I will ask Professor Dilip Mukhopadhyay, sir, if you have any comments on Chirantan's work. He has done a volume.
I have interacted with Professor Dilip Mukhopadhyay a couple of times, and he has been given some good creative feedbacks earlier as well. And I'd love to hear from him right now as well. What will be his?
Yes, there is no doubt about that. You have done a tremendous amount of work.
Thank you, sir.
There is no doubt about that. The quantum of work that you have done, and if you have done all by yourself,
yes,
for your PhD thesis is very commendable. Right? So yes, my few questions do not take away anything from you, from your contributions, your hard work. There's 2-3 points that I would like to mention here, not a serious question. First of all, that typical outcrop pattern of Sikkim Himalayas, particularly between MBT and Taken sequences, the outcrop pattern needs to be explained in any kind of structural analysis. Number 2, about details about your work, is that there is one rock that is missing in your cross section, that is Linksenisis.
Linksenisis, yeah.
Right. Linksenisis, they occur at several levels, several structural levels, and they also mimic the outcrop pattern, the whole thing. And finally, that your cross section, in part at least, are parallel to thrust trajectories, thrust traces.
Yes.
So these are a few comments that I have to.
Yes. So regarding the first comment, which is about the outcrop patterns, are you talking about the north-south fold and the
overall outcrop pattern?
Overall outcrop pattern. So so that has been explained by there are two different school of thoughts. One comes from Professor Bose's work, where they have explained through folding mechanisms, and the way Professor Bhattacharya has explained that there was a blunt culmination that happened due to the formation of the elongate duplex, which kind of folded the overlying thrust sheets along a north-south trending fold. Regarding the Linxenis, I kind of treated the Pelling thrust undifferentiated, like it's my mistakes. I should have marked the Linxenis because that's something I have seen it. I have in the field and I have mapped it, and I should have done that. But here I should have given that disclaimer that I have treated it undifferentiated, the Linxe and the Paronis here. Regarding the thrust, what was the so the thrust structures parallel to the foliation? That was your last question.
Your line of sections are at some parts at least are subparallel to the thrust sheets or thrusting.
See here, so they are
the central part of your section, right?
So they are actually it has been actually folded by that north-south antiforms. As a result, they have a little easterly. So I have a northeasterly dipping marked them this part where it was dipping northeasterly. So I kind of used it, which was sub-horizontal along the line of cross section, because actually it has a much more easterly component. Because it started out as a north.
Chirantan, just to tell you, look everywhere, even where the thrust sheet is trending north-south, the lineation is north-south.
Yes, that is there.
So
yes.
That is the thing, when you have a lineation north-south, even though the thrust sheet trending north-south. So that's the reason of what we said, this could be due to the buckling. You understand what I mean? The thrust sheet folded by buckling.
Yes. Yes, I get what you're trying to say. So the third point, I think, so at certain place it was not it was kind of not exactly parallel to as it should be, in typical drawing cross sections, because it should be perpendicular. But as it has been folded in different order, especially the north-south fold has kind of modified the thrust traces, the overline, the thrust sheets which are lying on top of the elongate duplex, kind of folded along, has been refolded along a north-south fold tending antiform. So as a result, they have kind of they are not really that perpendicular. They have kind of becoming subparallel. But the effect of as a result, they are kind of portrayed as a more of a horizontally dipping thrust, where it is, but they kind of picked up the deep kind of again become much more steeper as we move up from that part, and so that's how I kind of constrained it. Answer your question.
Finally, if you look at this the Sikkim Himalayas, the large part of the area have been affected by metamorphism. Okay. And balancing cross section had been successful in sedimentary terrains, where there is no internal strain at all. This balanced cross section in the Himalaya, in the Sikkim Himalayas, could only be effective because if it is highly ductile deformation, all that balancing cross section does not really work all that well. You know that very well. Now, in this part, in the Sikkim Himalayas, metamorphism is much earlier than thrust tectonics.
Yes.
Right? So, if that is so, then the quartz orientations, how can that be used as kinematically related to the thrust force? Because thrusting has nothing to do with the metamorphism. And if there is no metamorphism during thrusting, then how the rocks were metamorphosed at all? They must have been metamorphosed earlier than that.
Yes, so I think one of
This we have shown very conclusively. We have shown very, very conclusively.
yes. So your just to clarify, the question. So your question is about if so. The first part of your question is how can we extend the concept of constructing a balanced cross section into the interior part of an orogen where there is lot of metamorphic rocks. Is that the question? The first part of the question?
That's a serious problem for everybody, for you, for me, for everybody in this world.
I think if there is ductile deformation, the method of drawing cross section becomes very dicey.
Right.
So typically, the what was suggested for obviously, as Professor Mukhopadhyay said, it was initially for the sedimentary part of the orogen, which did not record plastic deformation or recorded intense metamorphism. So that's why the initial balance was.
Chirantan, that is one of the fundamental assumptions of drawing balanced cross sections, that there is no ductile deformation.
Yes, so there is also
your restoration and then they lose all meaning.
Yes, so that was the thing that was mentioned, that there is no change in the bent length. So what if you, along with the balanced cross section, so the concept of balanced cross section, if you think about it, is it's actually looking at it inverting the deformation. Okay, so inverting all the components of deformation, whether it is translation, rotation. So typically when we construct a balanced cross sections, we are actually just looking at the translation component and the rotation component of deformation.
Let's get back to the issue. As Professor Mukhopadhyay said, the other senior Mukhopadhyay, that if there is any ductile deformation, if there is a lot of internal strain, then drawing a balanced cross section is extremely difficult and loses its meaning altogether.
Yes.
In Sikkim, it could only be done because of metamorphism, during which there will be ductile deformation and all that are much earlier.
Much earlier, yes.
Than your thrust tectonics. Okay? So because that's why it could be done. But my question is, if that is true, metamorphism is earlier than thrust tectonics, then how do you relate the metamorphic fabric to thrust tectonics?
Absolutely.
Metamorphic fabric is much earlier.
Yes.
And your thrust tectonics is much later.
Yes.
It's something that needs to be thought about.
Yes.
How can you use that?
I'll try to answer that. So, as you correctly said, the penetrative strain fabric is actually parallel to the dominant foliation, which is for if we go towards either the cystose foliation or phyletic or gneissic foliation. So along those foliations, we see stretched quartz grains. So they are actually the tectonic foliation. So, and they are as the stream data suggests, they are prior to the thrusting, and also the metamorphic, the prograde metamorphic ages suggest, the metamorphism happened prior to the thrusting event for MCT, also for PT. So now the stream that I have measured in terms of the orientation it's tracking is pre-thrusting. So one of the way the metamorphism has happened is through the overburden that's happening due to the thickening of the crust. So the grain scale shortening that I have measured is related to the Himalayan orogeny, not just related to the thrusting. So if I'm just measuring thrust related strain, so I should be only looking at within the shear zones, where actually we are seeing obviously those early fabric will be lost completely due to the intense deformation within the shear zone. And those strains are actually giving the thrusting related strain. But the moment you are out of the shear zone, the strain is dominantly controlled by the tectonic fabric, which is pre-thrusting. So the way
So that is precisely the point, Chirantan. But the balanced cross section that you are drawing, the shortening that you are calculating here is essentially thrust related. It is not pre-thrusting strain, right? So comparing these two and adding up these two, does it make sense?
See, so when I was actually trying to look at the missing shortening, so it's the shortening that has occurred during the entire Himalayan orogeny, which started some 50, 60 million years back. So although, like if it has formed prior to thrusting, the grain scale shortening, but that is something forming that grain scale. The penetrative strain fabric is forming during the Himalayan orogeny. So that's how I looked at it. But when I was undeforming thrust sheets, I was removing all the components of deformation. So so the different components are translation, rotation, and strain. So apart from just the translation and rotation, I also unstrained the thrust sheet to see, because as it has recorded strong penetrative deformation, so the bed lengths have changed as well. So that's why
Chirantan, that strain, if it preceded the thrusting, how can you unstrain the thrust sheet?
Okay, I understand.
So that strain lies within the thrust sheet. So that's not really a strain that is happening due to the thrusting event, but that is something remains within the thrust sheet pre-thrusting strain. So
but your individual.
I have a very simple comment. Both the aspects of your study, the balanced cross section and your strain measurements from the quartz grains, they assume they are based on some assumptions. You have assumed something when you draw the balanced cross.
Yes.
So I would have been happy if you had listed for both your drawing of the cross section and for your strain measurements. Would have been happy if you had listed all the assumptions that you have made in following that study, in carrying out that study, and then we could have gone by each item of your assumption, that how scientifically valid the construction is. So this is just a comment, it's not a question.
So thank you I'll definitely incorporate that into future presentation. Yeah, I think that's a very valid suggestion.
Since I started it, I reiterate that your presentation incorporates a tremendous amount of really very voluminous work. So for that I congratulate you.
Yes, he is to be congratulated for the work that he has done.
We are just commenting. We are not.
Yes, sir, obviously, it's a
we are just
discussion.
discussing and commenting on your presentation. But your presentation is excellent. About that, there is no doubt. It is just comments, few comments.
Yes, sir.
If you give a talk and if there is no question, you feel very bad.
Yeah, true.
So that's how it goes.
Yes, sir.
So any more queries from
Yes,
other people?
Chirantan, there is one query written from Orindam Shortcut in the chat box.
Yeah.
You can read it by yourself. Can you open the chat box, Chirantan? Or shall I read it for you?
I think I will be able to open this, yeah.
Yeah.
Orindam
Orindam also raised his hand. So is it the same question that you have, Orindam, or something else?
No, same question.
Okay.
I thought it will be finished, that's why I...
No. we will take your question, then we will finish.
Can you read out the question?
Yes, I can read out. We all know hanging wall of MBT is associated with Gondwana sandstone, and you have measured strain from these rocks. As we all know that ductile deformation is associated with metamorphism, are these quartzite rocks, but named as sandstone. So in the hanging wall of MBT, we don't have the rocks are not metamorphosed, so they are sandstones only, and the strain that I have measured, that is the deformation within the sandstone for MBT.
Hanging wall of MBT.
Yes, sir. The hanging wall of MBT is actually carrying
You have quartzite, right?
the rocks that I have encountered in the hanging wall of MBT between MBT and Ramgarh Trust.
You have phyllite, you have quartzite, right?
So yes, sir. So those are actually in the hanging wall of other trusts, which are. Let me show you. Yeah, let me go to the map. I think. So see, the MBT trust is actually this yellow color little tiny sliver that you can see. So which are actually composed of unmetamorphosed sandstones and slates, carbonaceous, not carbonaceous, sorry, slates and sandstones. So the quartzites and phyllites that you were talking about. So these are green, the green units. So which lies in the hanging wall of other trusts. Yes.
But point is that always metamorphism is associated with the ductile deformation, right? That means whenever you are measuring a drop deformed by ductile deformation, it should not be sandstone, isn't it?
Yes, sir. So in those rocks, actually, I'm measuring deformation associated with plastic deformation. So this is not just metamorphism related. So these are tectonic foliations, because apart from those the micaceous minerals, there are prismatic minerals like quartz. Of course, they are also recording stretching along those. So they are deformed tectonic foliations, and the deformation or the metamorphism is happening due to the overburden of the hanging wall of thrust sheet, which are kind of burning the footwall rocks. So the strain that I have measured from these rocks is the deformation of quartz associated with plastic deformations, the plastic deformation, which may be which is earlier than the thrusting event, but that's still part of the deformation, the Himalayan deformation.
That means in this case, you are not measuring a strain of ductile deformation, right? Am I right? I don't know, basically.
I'm measuring strain. So the term ductile is it's a scale dependent terminology. So yes, I'm measuring strain due to the crystal plastic.
Theoretical terminology.
Of course, I'll come from a mechanism point of view, like the deformation mechanism point of view, where the quartz grains are recording crystal plastic deformation. They are plastically deformed, with the microstructures will be like undulose extinction, recrystallization, subgrain formations, which typically occurs in quartz greater than 300 degrees centigrade temperature.
If I'm not wrong, that means
wouldn't 300 degrees centigrade wouldn't that metamorphose the rock?
So that will be like very low green cyst phases kind of metamorphism.
So it is metamorphism.
Yeah. So simultaneously it is happening, sir.
You cannot say it is unmetamorphosed.
No. I'm not saying that. Sorry if I there is a miscommunication. I'm saying the deformation and metamorphism happening simultaneously. It's not just the metamorphism alone. There was simultaneously deformation going on because of the burial of the thrust sheets due to the very thick thrust sheets were being emplaced on top of footwall rocks.
May I add something?
Yeah.
That if you look at Biot-Ramberg equation, there is no temperature. It is a viscosity contrast that gives you buckle fold.
Absolutely.
We all know that. Now, viscosity contrast does not necessarily mean it has to be metamorphosed, because there are excellent buccal folds in many sedimentary terrains. Many sedimentary terrains.
Yes.
So we really don't need metamorphism always. Of course, there is a metamorphism and then there is a deformation and buccal folds also. But it is not necessary always that we have to have a metamorphism to develop buccal folds. It all depends on the viscosity contrast.
Yeah.
That
Just
is
to
completely correct, Dilip.
Well,
If it is 300 degrees centigrade, the rock would be in a metamorphic state.
yeah, that's
Yes.
true. That's true.
That's true.
That's what I wanted to say.
But then there are many situations, as you know much better than I know,
Yes.
that there are many places in sedimentary rocks where temperature was not 360 degrees.
Yes, and
much
they
less.
have permanent deformation, folds are developed.
Right.
Yes.
Whatever the mechanism of folding, but
Air flow and all these things, they can take place in absolutely sedimentary rocks.
Yeah, that's true. If you go to Jagros, you will see this type of folds.
yeah.
You don't need
And
metamorphosis.
Santanagos makes folds like that all the time.
And just to add, like even in the Shivalik rocks also, like, we
Yeah.
see folding, which
Yeah.
are very shallow.
Any more queries from other people? If not, it's really, we must be thankful to Chirantan. It's a long time.
Thank you, sir. I'm going.
Wonderful talk. Excellent.
Thank you, sir.
We're so happy.
Thank you, sir.
Congratulations for the amount of work that you have done.
Thank
Yeah.
you, sir.
Yes.
Means a lot, sir.
Really, really, really good.
Thank you.
So, if not, then we should give a big round of applause to
Ah,
Chandan.
Thank you, sir.
It would be good if you can open your video footage of all of our faces. Thank you, Chirantan.
Thank you, sir. So I'm
Come
going
to
to.
presidency sometime.
Yes, sir. I'd love to.
Okay,
Thank you,
this is
sir.
a personal invitation.
Thank you, sir.
Okay. So thank you very much, everyone. We'll meet again next month, and wish you have a very good start of a new year.
thank you.
Thank you.
Happy New Year in advance. Thank
Happy
you.
New Year.
Thank you, everyone.
You have to say something?
No. I mean, thank you very much, Chirantan, for accepting
Thank you.
the invitation. I mean, I think you had your second PhD Viva today.
Yes, I think it was a much bigger than the earlier one.
I hope you can incorporate some of
Yes.
the comments for
Yes,
your
I
future
will.
research, and some value will be added to your thinking process as well. So thank you once more, and wish you all the best in Australia.
Thank
And
you.
thank you everyone for attending the talk, and we will circulate the next January's e-lecture topic and date and time very soon. Thank you.
Thank you very much.
Bye.
Bye-bye.